Welcome everyone. We are going to talk about direct self-tuning regulators, and by direct I mean that the estimator will directly estimate the parameters of the controller. We'll see that in a moment. Now let's first consider a single input, single output block diagram for a system. This is a plant. This is a feedback component of the control law, and this is the feed forward component. B and A are polynomials in the forward shift operator Q. Also S, R and T are polynomials in the forward shift operator Q. Now if we do this, we can calculate the closed loop transfer function of the system. So that will be equal to BT over AR plus BS. And typically we factorize the zeros or the numerator of the plant into two components. One component which is monic, this is called B plus, and it contains zeros to be cancelled from the system. So here zeros to cancel, while B minus will contain the rest of the polynomial B. The relation between the output and the set point should follow a reference model. So Bm over M here, that gives the reference model. Which is designed according to some specifications. The closed loop characteristic polynomial of the closed loop system is given by AR plus BS, and that can be shown to be equal to some polynomial A naught, we call that the observer polynomial, times AM, which is the denominator of the reference model, times the B plus, and this is the factor that contains the zeros to be cancelled from the original system. Now this equation is called the Diophantine equation. And it has to be solved for the unknown polynomials R and S, and once that is done, part of the control law is calculated. The other polynomial that completes the control design is T, and that polynomial T is equal to the numerator of the reference model times the observer polynomial divided by the remaining part of the original plant that has not been cancelled. And as we mentioned before, the polynomial Bm should contain B minus as a factor. So if we divide, the result would be some polynomial or a constant. We call it here Bm bar, and that is multiplied by the observer polynomial. Just a hint here, it's clear from the characteristic polynomial that the closed loop poles will be at the roots of the observer polynomial, the roots of the poles of the reference model, and the zeros to be cancelled from the original plant. And that means that we cannot cancel non-minimum phase zeros or zeros that are outside the unit circle, because that's obviously will lead to instability. If we design R, S and T, we can calculate the control law as the polynomial R times U equals the polynomial T times the set point minus the polynomial S times the feedback signal Y. From this equation we can calculate the value of the control signal at a given sample, and that would be applied to this. Now our purpose is to see how we would use direct self-tuning regulators, which means that how to rewrite the equation so that we can estimate the parameters of the controllers directly using the estimator. So I'm going to start from the Diophantine equation. I will write R as R dash times b plus. We know that if we want to cancel a certain factor b plus, then it has to be a factor in R plus. We factorize b into b plus times b node. I'm going to assume that I'm canceling all the process zeros, and since b plus is a monic polynomial, so what's left will be either 1 or a constant b node. This is corresponding to b minus, and that should be equal to a node times am times b plus. Now I can cancel out b plus from the whole equation. Then I will multiply both equations by y of t. So if I do that, I will get a r dash y of t plus, here there should be s, b node s y of t is equal to a node am times y of t. Now I know that the product a times y from the original block diagram, this is y and this is u. So a times y should be equal b times u. So I will just substitute for ay by b times u plus b node s y of t, and that should be equal to a node am y of t. Okay, now we can write an expression for y of t as 1 over a node am. I can factorize b as b plus times b node, and we know that r dash times b plus is r, so that will give me r times u of t times b node plus b node s y of t. So now we would like to put this equation in a form that the estimator can use, and that can be done if we consider a node by am as a filter that is ut and y of t have to go through it, and the result, the filtered value, will be processed by the polynomials r and s. Actually, in order to do that, we have to rewrite r, s, a node, and am in terms of the backward shift operator, so that we can calculate the values in terms of previous signal values. So if we do this, we will get r star, and I put the star here to refer to the fact that this is in the backward shift operator q to the minus 1 instead of q, times the filtered signal u plus b node s star times the filtered signal y. We'll see by example how to put that in a form that the estimator can utilize to calculate the coefficients of the polynomials r and s. Let's consider an example to show how to implement a direct self-tuning regulator. I'm going to consider a second order system where the parameters b, a1 and a2 are unknown, and the reference model is given by a first order transfer function, and of course the parameters bm and am are given, they are known. So in order to do the design, if we assume that all process zeros are cancelled. Then we can write B as a product of B plus times B node. In our case here, since the B polynomial is monic, then B node is equal to 1. So B plus will be equal to Q plus B. Now if we consider the Diophantine equation, AR dash plus B node S equals A node times AM. Again, B node is equal to 1. Then the degree of S is equal to the degree of A minus 1, and that will give me 1. And degree of R will be equal to the degree of S equals 1 again. So that means that the degree of R dash, which is the degree of R minus the degree of B plus, will be equal to 0. So now I know the degree of R dash, it is 0, and actually R dash is normally a monic polynomial, so I can take R dash equal to 1. And then I will have S with first order and A node and AM. I can conclude from that the degree of the observer polynomial. So the degree of A node will be equal to the degree of A plus degree of R dash minus the degree of AM. The degree of A is 2, the degree of R dash is 0, the degree of AM is 1, so that will give me 1, which means that I can choose A node as a first order polynomial. I'm going to take it equal to Q for simplicity. Now I know from what we did before the expression for y of t, so I'm going to rewrite that. So y of t will be equal to 1 over A node AM. This is multiplying R times B node U of t minus S times B node Y of t. Again, B node is equal to 1. This is equal to 1. So I'm going to substitute here for A node and AM. That would be 1 over Q. AM is Q plus AM. And that multiplies R. And R is Q plus B times U of t minus S. S is a first order polynomial. It is S node, some constant S node times Q plus S1, and that multiplies Y of t. Now the point here is to rewrite this equation in terms of the backward shift operator Q to the minus 1. So we just look at the degree of the product A node times AM. You'll find it second degree. So I'm going to multiply up and down by Q to the minus 2. So that will give me 1 over 1 plus AM Q to the minus 1. And here I will have Q to the minus 1 plus B Q to the minus 2. That multiplies U of t minus S node Q to the minus 1 plus S1 Q to the minus 2. That multiplies Y of t. Okay. So this can be written as Q to the minus 1 plus B Q to the minus 2 times the filtered signal of U minus S node q to the minus 1 plus S1 q to the minus 2, the filtered signal of y. We'll see how to calculate the filtered signals in a moment, but for now let us rewrite this equation as a difference equation that will give me the filtered signal t minus 1 plus b, the filtered signal t minus 2, minus S node, the filtered signal of y at t minus 1, minus S1, the filtered signal t minus 2. Now, since this term doesn't have any unknown parameter, I can bring it to the left-hand side of the equation. So I would write, this is, by the way, is y of t, the left-hand side. So I could write y of t minus the filtered signal of u at t minus 1 equal a product. That product would contain uf t minus 2 y minus yf t minus 1 and minus yf t minus 2 times the parameters b, S node and S1. So this is our form for the estimator. The left hand side here is what is corresponding to what we used to call it as the output measurement, but in this case it is just y minus the filtered signal uf at t minus 1, and this is what we used to call phi. This is the regressor vector, and here this is the unknown parameters b, S node and S1, and as you can see these are directly the parameters of the controller. So if we can calculate theta, we can just plug in them into the control law and we can calculate the control signal. However, before we do this, let's first see how to calculate the filtered signals. So the filtered signal can be calculated as follows from the definition that we have for, say, yf t minus 1. It is equal to 1 over 1 plus am q to the minus 1 u t minus 1. This comes from here. This is ut and this is the filter. So the product of these two will give me the filtered signal. But from this equation we can write that the filtered signal at t minus 1 equals minus am, the filtered signal at t minus 2, plus ut minus 1. And similarly we can find an expression for the filtered signal yf. So that will be yt minus 1 minus am, the filtered signal at t minus 2. So from these two expressions we can calculate always the filtered signals, and we use them in the regressor when we need them during the calculations. So this way we can calculate, as I said, using the recursive least square, we can calculate the parameters b, S node and S1 at each sample. Now let's see the control law and how it will be calculated. We know that the control law will be equal to the estimate of r times u. That should be equal to t hat times the set point minus s hat times y. Now what is the expression for t would be equal to the reference model numerator polynomial times the observer, and that's divided by b minus. In our problem here, b minus is equal to 1, and it is given that bm is equal to just a constant, small bm, and q is corresponding to a node. So that will give us bm times q. So if we substitute then in the expression for the control law, we get q plus the estimate of b, this is the R polynomial, times u of t, equals bm times q, this is the t polynomial, times the set point, minus the estimate of S node q plus S1 times y of t. So again we can write, we can multiply both sides of the equation by q to the minus 1 to get an expression for u of t in terms of the previous values of the other signals. So we can write then u of t equals minus b hat ut minus 1 plus bm, the set point t, minus the estimate of S node times y of t, minus the estimate of S1, this is estimate, yt minus 1. So this is the control law, and as we can see, it depends on the estimated parameters b hat, S node hat, and S1 hat, and that what makes it a direct self-tuning regulator. Well, if we implement the previous example as a direct self-tuning regulator, we can adopt the following algorithm. First, we are going to initialize the parameters b hat of 0, S node hat of 0, and S1 hat of 0. And of course, we will have the covariance matrix 3 by 3. Then at each sample, we will do the following. We will measure the output of the plant. We calculate the filtered signals YF and UF. And then we construct the regressor vector phi of t. Then we execute the recursive least square algorithm to find the estimated values of b hat, S node hat, and S1 hat. And finally, we calculate the control signal. And in the next sample, we will do the same procedure again. Let's now move to the case where we don't want to cancel all the process zeros. Maybe some of them are outside the unit circle, so they are non-minimum phase zeros, and that's why we don't want to cancel them. Or maybe because they are very close to the unit circle, and their cancellation may lead to a very high oscillation in the control signal. So we'll start again by considering the Diophantine equation, AR plus BS equals A node, the observer polynomial, times AM times B plus. In that case, we will consider B consisting of two factors, B plus and B minus, where in this case B minus will contain some zeros, as I said, maybe outside the unit circle. Now we can factorize R as before as R dash times B plus the factors of B plus times B minus times S. This will be equal to A node AM B plus. We are doing the same actually sequence as we did before when we derived the direct self-tuning regulator. I'm going to multiply by y at both sides of the equation. So I will get here ar dash y plus b minus s times y equals a node am times y. And again, a times y is just can be substituted for by b times u plus b minus s y of t, and that will be equal to a node am times y of t. And again, b is b plus times b minus, so b plus times r dash, this is r, so I get here r times b minus line ut plus b minus s y of t, and that's equal to a node am y of t. Now I can write y of t as 1 over a node am times, now the multiplication of r times b minus, I will call that r bar times u of t, and the multiplication of b minus times s, I will call that s bar, so that's plus s bar times y of t. And we'll do what we did before. We will assume that this is a filter, and u of t or y of t will go through that filter to obtain a filtered signal uf and yf, and r bar and s bar will be the polynomials that will appear in the equation for the estimator. So we can write r bar star. I'm doing the star here to remind ourselves that this is in the backward shift operator, and I will get the filtered signal. Normally this would be minus d naught, and d naught here is the delay in the system. As I mentioned before, the delay would be the difference between the degree of the denominator and the numerator of the plant. And here I will have s bar star times again the filtered signal. Now this is a form that can be written as a regressor times the unknown parameters. Now the unknown parameters will be the parameters of r bar star and s bar star, so I will get the parameters here. However, we notice here that the uncancelled zeros b minus will appear as common factor in r and s. So when we do the recursive least square algorithm, we have to look for the common factors between the resulting r and s polynomials, and then cancel that out before we implement the controller. So this is the basic difference between the two cases. Here, in case of not cancelling some of the process zeros, these zeros that have not been cancelled will appear as common factors in the polynomials r and s. So there should be an intermediate step to cancel them out before we conclude the actual parameters that can be used in implementing the controller. Okay, so this actually ends my lecture on the self-tuning regulator, both for the direct and the indirect cases. Thank you.